Welcome back to the Terradome people. We're going to continue this course discussing the topic of vectors. In this course, we will work with two types of mathematical quantities. Those are scalars and vectors. A scalar is a type of quantity that only possesses a magnitude. Another way of phrasing that is if you want to fully specify everything you need to know what a scalar quantity is, you only need one single number. For example, I only need one number to fully specify an object's temperature. I only need one number to fully specify an object's mass, and so on. On the other hand, a vector in this course we will say is a type of quantity that possesses both a magnitude and a direction. So a vector is inherently a different type of mathematical object from a scalar. Some examples of vectors that we have already considered are position and velocity, and some other types of vectors that we will work with soon include force and momentum. Another way of describing what is a vector is to fully know everything there is to know about a vector. To fully specify a vector, you need a list of numbers. One number alone is not enough to fully specify a vector. Now, if you're curious, just out of sheer wanting to know more, there also exist these mathematical objects called tensors that are common in some upper level physics courses. The formal definition of a tensor is defined by the way it transforms when you look at it from one perspective versus another perspective. That is somewhat of an ambiguous way to define what a tensor is. One way of thinking about a tensor is not all matrices are tensors, but all tensors can be represented with matrices. A matrix is a list of entries with rows and columns, sometimes more than that. But in this course, we're not going to consider tensors. A scalar and a vector, though, are some examples of types of tensors. So, as an example, a scalar quantity we said is speed. Speed could fully be described by just a single number. If you know something is moving at 5 meters per second, you know everything there is to know about that object's speed. A vector quantity, to fully specify it, you need to specify both the magnitude and the direction of that quantity. So saying just 5 meters a second is not enough to specify velocity. Saying 5 meters per second to the north is enough to specify an object's velocity. I can specify velocity vector by saying 5 meters per second to the north. Now, in the previous slide, I said one way of thinking about vectors is you need a list of numbers. You need more than one single number to fully specify a vector. How would I think about it with this example? Well, instead of saying 5 meters per second to the north, what if I said the object's speed is 5 meters per second to the north and 0 meters per second to the east? Now you know you are moving 5 meters a second north, 0 meters per second to the east. You have now given me the list of numbers that is enough to specify this velocity vector that I wrote over here. So 5 and 0 are that list of numbers. In the text, vectors are written in bold, and they also are denoted by having this arrow above them. So vectors have the arrow above them. Scalars do not have the arrow above them. In the previous chapter, we did implicitly work with vectors. If you think about how we treated velocity, when an object is moving in the positive direction, that object's velocity was a positive number. When an object is moving in the negative direction, that object's velocity was a negative number. So to an extent, we kind of began working with vectors in the previous chapter, but we're really going to start working with them for a few chapters now. Now, north and east are not always the most practical directions to use in a meaningful way. So usually what we will do is we will set up a Cartesian coordinate system. And as always, you are allowed to set up your Cartesian coordinate system. You are allowed to set your origin and the directions of the X and Y axes to point however you want. You could choose whatever is convenient based on what's going on in the particular problem. Now, it is not impossible that you might also need to work with a third direction, z, because we do live in a 3 spatial dimension universe, but it is highly unlikely you will see z in this course. It technically is there, but it doesn't really add anything new to what we're doing. Nearly everything we do will just be in 2D with x and y. Also, very important, something I tried to stress in the previous chapter was once you set up your coordinate system, be consistent. If you set up a coordinate system, you say, here's the origin, here's the positive x direction, there's the positive y direction. You're not allowed to change that in the middle of a problem. Once you specify it, you need to stay with it for the rest of the problem. If you choose to specify that the positive y direction points up, then any vector that is overall oriented upward will have a positive y component, and any vector that is overall oriented downward will have a negative y component. So the y component of a vector might be positive or negative depending if it overall points up versus overall points down. Now, if you want another video that will be following this one in the PHY 121 playlist, comes from the YouTube channel 3 Blue 1 Brown. The author of this video made some very nice math videos. And vectors, what are they? It's the first video in a series of video introducing you to linear algebra. If making mad money is something you're interested in, then being a math major, linear algebra is a very effective way to go to do that. Linear algebra is a branch of mathematics that works with vectors a lot. Vectors can be thought of as something with a magnitude and a direction, which is commonly the case in physics. In computer science, vectors can be thought of as a list of things, and both of these pictures of vectors are equally valid. It's not to say one is better than the other. But this video, it's only about 10 minutes long. It has some nice animations, and it really gives you a good feel for what vectors are. So I would recommend watching it. So here's an example of a vector. I drew something that has both a magnitude and a direction. This vector r has a magnitude. You could picture taking a ruler, putting a ruler up to your computer screen and measuring how long this vector r is. That would be the magnitude of the vector. You also see the vector is pointing up and to the right. So up and to the right, that is a valid concept for direction. Another way of specifying this vector's direction that is probably better for what we're doing is we could say vector r is pointing in the positive x direction and pointing in the positive y direction. The positive x direction because overall vector r is oriented to the right, and simultaneously positive y direction because overall vector r is pointed towards the positive y direction, oriented upward. Now specifically, if I want to know how far does this vector r extend to the right and how far does this vector r extend upward, I could compare. So I begin here and vector r extends 4 units to the right and vector r extends 6 units upward. So I would say the x component of r, that I denote r with a subscript x, is equal to 4. The y component of r, that I denote r with the subscript y, is equal to 6. So you could say if I were to begin at the tail of the vector, I walk 4 units to the right in the positive x direction, walk positive 4 in the x, and then walk positive 6 in the y. I will end up at the tip of the arrow of this vector. Now looking at this picture, you could just as equivalently say you're going to walk 6 units in the positive y direction and then walk 4 units in the positive x direction. That would also be just as good. So we denote Rx as 4, Ry as 6 in this picture. When you look at vectors, I would say look for right triangles contained within those vectors. This could be a very useful tool to help you work with vectors. Very often, not always, not 100% of the time, but very, very often, Rx and Ry will form the legs of a right triangle, and the vector r itself will form the hypotenuse of a right triangle. When this occurs, the hypotenuse will be the same as the magnitude of that vector. Over here in this picture, I very explicitly have a right triangle that is drawn. Our x of 4 units is one of the legs of the right triangle. Our y, which is 6 units, is the other leg of the right triangle. And then r is the hypotenuse of this right triangle, which is the magnitude of this vector r. Now, usually we will see that one of the two legs will coincide with one of the axes, either x-axis or y-axis, and the other leg of the right triangle will be parallel to the other axis, but shifted away from it some amount. So in this picture, our x coincides with the x-axis, our y lies parallel to the y-axis, but is shifted over by some amount. If instead I were to draw this right triangle something like this, I could say then our y would be coinciding with the y-axis and our x lies parallel to the x-axis but shifted upward by some amount. Now, vectors are mathematical objects, and if we're working with mathematical objects, we will want to do something with them. So we will want to perform certain mathematical operations with vectors, and one operation we're going to perform is addition. So one rule that we're going to follow is we are given if both a and b are vectors. I'm being ambiguous to what a, b, and c are in this slide, but if you know a and b are vectors, and if you know a plus b equals c, then c is also going to be a vector. This is basically saying when you add two vectors, you get a vector as your answer. Also, if you are given both p and q are scalars, and if p plus q is equal to r, then you are guaranteed r will also be a scalar. This is basically saying when you add two scalars together, you get back a scalar. If you think about it, if you add two numbers together, you get a number out as your answer. If I were to say 4 plus 16 equals triangle, well, that statement has no meaning. 4 and 16 are numbers. We work with numbers in mathematics. A triangle is a shape. We work with shapes in mathematics too. But you don't add two numbers and get a shape out, even though it's perfectly valid to work with numbers and it's perfectly valid to work with shapes. However, if I say 4 plus 16 equals 20, I add these numbers together and I get a number out. Similarly, we don't need to only work with numbers. We could think about positions. If I add 2 meters to the right and 3 meters to the right, those add together to give 5 meters to the right. In that way, it's kind of like I'm adding lengths together. A length is not the same as a number, but it is somewhat related to a number. So, is it ever possible to add vectors and scalars? In this course, the answer to that is no. You would be adding unlike and incompatible things. In some advanced areas of mathematics, there is a fully consistent way to add vectors and scalars together, even though they are different types of objects, and that's fine. But we are not going to come anywhere near that topic. So you're in that case, in this course, never add vectors and scalars together. So we have a notion of adding vectors, and we're going to show soon how you would actually go about doing that. What about subtracting vectors? If you think about what does it mean to subtract numbers, subtraction is really just the opposite of addition. Subtraction is not really a different mathematical operation from addition. When I subtract a minus b, I'm really saying a plus the opposite of b, or a plus negative b. The idea we present here is also going to apply to vectors. If I say vector p minus vector q, that's like saying vector p plus the opposite of vector q, or vector p plus negative vector q. So after we have a notion for how we will add vectors, and after we know how to write the opposite or the negative of a vector, we'll be able to subtract vectors just as easily as we'll be able to add them. So when we actually add vectors together, we add their components separately. let's suppose we have a coordinate system and we have vector A, and then here is vector B. I am going to add vector A to vector B. So if I add vector A plus B, if I want to use the graphical method of adding vectors, I could draw vector A with the tail of vector A beginning at the origin. Then I draw vector A, whatever magnitude it's supposed to be, whatever angle it should be oriented at. And then at the end of vector A, I draw the tip of the tail of vector B, and then I draw it whatever magnitude and angle vector B is supposed to be at. And then I connect the very beginning of vector A to the very end of vector B. And that will give me my sum of vector A plus vector B. So here's vector A plus vector B, gives me a new vector, begins at the very beginning of A to the very end of vector B, that I call vector C. So A plus B equals C. Now, what are the components of vector C? Well, let's look at the components of vector A and B. So vector A will have horizontal component AX, vector B will have horizontal component BX. And if I look at these and I compare them to the horizontal component of vector C, I notice that the horizontal component of AX added to the horizontal component of BX will give me the horizontal component of CX. The entire horizontal component of CX is AX plus BX. Notice I did not say anything about the vertical components. I only added the horizontal components of A and B to give me the horizontal components of C. Very similarly, I could look at exclusively the vertical components of these vectors. And I notice the vertical component of A plus the vertical component of B gives me the entire vertical component of A plus B. So AY plus BY is equal to CY. When we add the component vectors together, we do not mix X components with Y components. So if I say A plus B is equal to C, the components of vector C are given as CX is AX plus BX. That's entirely the horizontal components. And separately, CY is AY plus BY. This is entirely the vertical components. I do not mix any X components or Y components together. The method we will use on homeworks and exams in this course is adding the components of vectors together. We might need to use some trigonometry, some relationships between sine, cosine, the trig functions, Pythagorean theorem, angles, to find what these components are. We're never really going to use this graphical method because this graphical method is not very thorough. However, I do think the graphical method is useful for showing a pictorial representation of what it looks like when we add vectors together. So in the next video, watch 3 Blue, 1 Brown, Essence of Linear Algebra, What Vectors Really Are. It's a very well-made video and it's only about 10 minutes long. And then we'll show some example problems demonstrating vectors, breaking them into their components using trigonometry, adding and subtracting vectors.